Okay, so today we're going to be talking about analysis of variance, or ANOVA, and specifically one-way independent samples, ANOVA. So for this lecture, we're going to conceptualize ANOVA and provide a short example of what a one-way ANOVA is. So let's take a second to recap. So we've gone over t-tests, and what t-tests do is compare means of samples, right? And so this indicates whether there are differences in the mean due to some sort of sampling error. So that's what t-test looks at, is whether or not there are differences based on sampling error. We also calculated effect sizes, so this indicates the magnitude of an independent sample's impact. We've discussed confidence intervals, which estimates a population's parameters, so the mean of a population based on a sample's parameters, or mean and standard deviation. So ANOVA is a little bit different than each of these. And we call it ANOVA because it's analysis of variance, so ANOVA, that's where we get the ANOVA from. And specifically, independent samples ANOVA and one-way ANOVA compares means from two or more independent samples. Okay, so this is where we sort of extend past t-tests, because t-tests can only look at two independent samples. ANOVA, on the other hand, extends beyond that and looks at two or more independent samples. So it's very similar to an independent samples t-test, where it can compare two groups or samples, right? But there's There's a slight difference here. What analysis of variance does is it analyzes the variance between mean scores. So the variability in those scores, meaning the extent to which people score differently from one another, and how those differences in scores can create statistical significance. So what it does is it examines the variabilities of scores both within a particular group and between particular groups. So these groups are the independent variable conditions, right? So the various groups mean that they're part of some sort of independent variable. So let's take another look at independent samples t-test. Remember, we have two samples here, and what we're doing is essentially comparing means across the two samples divided by sampling error, right? Standard error of the mean. ANOVA, on the other hand, we still have our two populations and our two samples coming out of two different populations, and we compare means across two or more samples, but that is divided by the variability within groups. Okay, so the extent to which people within each of these two samples vary on their scores for whatever outcome we're looking at. So there are three basic elements of variance. There's measurement error, and that's the difference between reality and how reality is measured. Right? So let's take an example. A person's love for candy versus how we measure somebody's love for candy. So a person's love for candy is reality, and how we measure that is how we measure reality. We can't always accurately measure reality. Oftentimes we can't accurately measure reality at all. So that's measurement error. The difference between what reality is and how we actually measure reality. Individual differences, that's simply the natural difference between people. People's differences in the extent to which they love candy, right? That's a natural sort of individual difference. And then finally we have the treatment or group effect. And that's the variance of scores due to some treatment group or group effect, right? So you being part of some specific group will affect your love for candy, for example. And so in one-way ANOVA, we're trying to model each of these elements of variance. We're trying to account for each of these elements of variance: measurement error, individual differences, and treatment effects. And the big guy we're trying to isolate is the treatment effect, whether or not the treatment effect actually did something or the group effect actually did something, because that's the piece that we're interested in. So again, this is the main piece that we're interested in, this treatment or group effect, right? So if we take this is a conceptual formula of this F-statistic, right? So remember back when we were doing Z-scores of the sample mean, t-tests, this is similar to those two. This is the F-statistic. This is conceptual formula of the F-statistics. We're not getting into the actual formula yet. So the F-statistic is similar to the Z-score and the t-test, where we're using that to compare to some critical value, right? So what we're looking at, the F-statistic is basically the variability between treatment groups or treatment conditions divided by the variability within treatment conditions. So in effect, what we're doing is we're looking at the treatment effect or group effect, the individual differences, and the measurement error, and dividing that by the individual differences in the measurement error. And what we're doing is we're sorting out this treatment effect, right? Because each of these are counted for, individual differences and measurement error are both accounted for in the numerator and denominator, which means they cancel each other out, right? So this is the main thing we're looking at. We're looking for the treatment effect here. So let's give an example. Mars is interested in launching a new color for their M&MS line. To do so, they're going to experiment with 3 colors, pink, purple, and light tan, to identify which color is most attractive to consumers. To see which color is most attractive, Mars places consumers in one of 3 rooms, the pink, purple, and light tan rooms, respectively. Each room has a bowl of pink, purple, or light tan colored M&Ms, right? So people walk into the room, there's a bowl of pink M&Ms, or a bowl of purple M&Ms, or a bowl of light tan M&Ms. To measure M&M color attractiveness, they count the number of M&Ms eaten for each participant. Okay, so each consumer walks into a room, they're sat down with a bowl of M&Ms of a particular color, and people measure to see how many M&Ms are eaten from that specific individual. So here we have the independent variable are the 3 M&M colors, right? So these can be considered the treatment if we're thinking of it in sort of clinical terms. So these are 3 groups or treatment conditions, right? So we have pink, purple, and light tan. Those are the 3 colors that people are given. We have a dependent variable, which is M&M attractiveness. So we're measuring M&M attractiveness by the number of M&Ms eaten by participants. And so what we're looking for is the difference in the number of M&Ms that consumers ate between the various groups divided by the number of M&Ms that are eaten within the groups. And so this is where we're accounting for variability, right? This is what we're talking about when we're trying to model variability. So we're trying to account for those individual differences, the measurement differences, and really focusing on the groups themselves. So just to recap here, so to conceptualize, ANOVA compares mean scores of 2 or more independent samples by examining within and between group variability. So that's the main takeaway from this, is you're still doing a means comparison. You're just doing it slightly different than what you can do with the t-test. And additionally, you can do more than just 2 groups with ANOVA.